In this video, I'm going to discuss about this molecular orbital theory in chemical bonding. Yes, we have learned about this various theories which has been put forward in order to explain the bonding which is possible in the molecules. Yes, so why this molecular orbital theory has been put forward, because there are few drawbacks which are involved with this valence bond theory, that is VBT theory. And what are those drawbacks? Is valence bond theory is unable to explain like why He2 molecule does not exist, that is helium-2 molecule that does not exist in the diatomic form, and also the paramagnetism of this O2. That means O2 is paramagnetic in nature, and this could not be explained by VBT. In order to explain these drawbacks, in 1932, Hood and Mulliken came up with this molecular orbital theory, and which could explain these questions, answers to these questions here. Right. So according to the VBT, we know that if a particular atom or a molecule, the atoms, the atomic orbitals of atoms will hybridize, resulting in the formation of, for example, if you are taking BF3 here the boron atom, the atomic orbitals of this will hybridize, resulting in the formation of hybridized atomic orbitals, right? Hybridized atomic orbitals here. And this will form bonds with the fluorine atom. Right, so this is based on what the atomic orbitals, which are now they're belonging to the single atom, and they are forming the bonds with another atom. Right, but here, according to the molecular orbital theory, now here the atomic orbitals now they do not belong, the electrons here will not belong to the single atoms, they belong to the molecule as a whole. So how is this possible? The electrons now no longer belong to the single atom, according, as it was explained in VBT. Now, here the valence electrons are considered to be associated with all the atoms in a molecule. That means the molecules, the atoms, the valence electrons of all these atoms together belong to, they're under the influence of all the four atoms here. That is what the molecular orbital theory is. So how could this be explained? According to this molecular orbital theory, now the atomic orbitals here will result in the formation of this molecular orbitals. Right. Now, first of all, here, let us understand that electrons has both wave nature and also the particle nature. Right. So it has particle nature and also the wave nature. Right. So according to the electrons in the atomic orbitals can be described by a wave function psi. This is a solution to the Schrodinger equation, right? So the electron in the particular atom, that means which is in the atomic orbital, now described with the wave function psi. Right. Now, if there are two atoms, suppose the electrons which are present in the atom A, the valence electrons described by wave function psi A, and the wave function of this atom B will be psi B. So what about the wave function of the molecular orbital? Right. So the wave function of the molecular orbital, that is psi A B. Right. How can this be obtained? That is the wave function of the molecular orbital. This wave function of the molecular orbital, psi AB, is obtained by the linear combination of these atomic orbitals. So the wave function of this molecular orbital, which is now psi AB, how can this be obtained? By the linear combination of this atomic orbital, which is called as Lcao method. Right. Let us look at what is this Lcao method is. That is linear combination of atomic orbitals. Right? Yes. Now consider two atoms A and B. Right. Described by the wave function, that is psi A and psi B. Right. Then the wave function of the molecular orbital, that is psi AB, can be obtained by what? The linear combination of these atomic orbitals, psi A and psi B. Right. Now here, which is under the influence of only single atom. Now the electrons in this belong to the molecule as a whole, and this is under the influence of the two atoms, that means on the molecule as a whole. As these atoms approach each other, then what happens? The the valence electron clouds will overlap, right? And the wave function of the molecule now can be described by the wave function psi AB, and this psi AB is given with the formula n into C1 psi A plus C2 psi B. Right. Now, what is n? This is called as normalizing constant, which gives the probability of finding the electron on the whole, which is equal to 1. Right. When what are the C1 and C2? C1 and C2 are called as the constants, which will give you the minimum energy for psi AB. This will give you the minimum energy for psi AB, and when the two atoms are same, that is when it's homonuclear, then C1 is equal to C2. Right. Now, what is the probability of finding the electron? The probability of finding the electron is the psi squared AB, and you know that. Now we can have this to be when n is 1, this one a square plus b square plus 2ab, that is C1 square plus a square plus 2ab. C1, C2, psi a, psi b plus a square plus 2ab plus b square. C2 square plus psi b square. Right. What about this term? This term gives the here, the first term, that is this term, is related to the probability of finding the electron on atom A. That is, finding the electron on atom A when it is an isolated atom. And this term will represent the, will give you, or is related to the probability of finding the electron on atom B when it is an isolated atom. And this term is very important, where it gives you the probability of the finding the electron when it is bonded. That means when the molecule is being formed. The more this value, that means if this value is more, if more, then the bonding is strong. So this is very important. Right. Now this is about this linear combination of atomic orbitals. Now, what will happen when s orbital combines with an s orbital? For example, hydrogen atom will have, so hydrogen we have only one is 1. So the electron is present only in an s orbital. So when a hydrogen molecule is being formed, that means s orbital overlaps with s orbital, or s orbital combines with an s orbital of another hydrogen atom. So what happens? Right. Now we have already said, so atom A, it is represented by wave function psi A, and there is an atom which is represented by the wave function psi B. And I said the wave function of this molecular orbital can be obtained by the linear combination of these atomic orbitals psi A and psi B. So how does this linear combination will take place? The linear combination can take place in 2 ways. Right, in 2 ways. What are those 2 ways? Either by addition of these atomic orbitals or by the subtraction. Right, so we can obtain this molecular orbital in 2 ways. Either these atoms can subtract or add. What does this mean? See, you know that the electron is described by a wave function. So this is the of the first atom, right? This is of the second atom. That means we are adding. That means what? The crest falls on crest and the trough falls on trough. That means it is a constructive interference. When there is a constructive interference, that means when addition, that means when the atomic orbitals are of the same sign. In other words, when the atomic orbitals are of the same sign, this is plus and this is plus. That means in phase overlap. That means constructive interference. That means crest falls on crest and trough falls on trough. Then it will result in the increase in the amplitude. This is an increase in the amplitude. So this is called as an in-phase overlap, and and giving a large resultant wave. This is a constructive interference. Now, if the so these two ways this can take place. That means addition, subtraction. What does the subtraction mean? The subtraction means that when the crest falls or trough falls on crest, that means destructive interference. That means now this is subtracting. This is the thing which is happening. Crest does not fall on crest, or trough does not fall on trough, then they cancel each other, resulting in the destructive interference. That, in other words, we are subtracting the atomic orbitals, out of phase interference. Both of these lobes are not of the same sign; they are of the opposite sign. So there are two types of combination here. So we know that the number of atomic orbitals combining will be always equal to the number of the molecular orbitals which are being formed. And these are the molecular orbitals which are being formed when s orbital combines with another s orbital of another atom. So what is happening when two atomic orbitals are combining, two molecular orbitals are being formed. And this here they can add or subtract. So when we are adding, that means in phase overlap, that is both the lobes are of the same sign. So this is the nucleus of these atoms, this is plus and this plus. When these two are combining, that is in phase overlap. So this is the of one atom and this is of another atom, psi A and psi B. That means in phase overlap, that means positive, both of them are positive sign, then they will get a molecular orbital here, which is represented by the wave function psi, and what am I writing here? G rate. I'll come to this, what is this G means later on. And when we are subtracting, that means when out of phase overlaps and the atomic orbitals are in out of phase, that means they are of the opposite side. These are the two atomic orbitals. This is the nuclei, one is plus and one is minus. So what do you get here? The two lobes, which are these two are the nuclei, and this is of plus and this is minus here. So these two lobes are opposite sign, where there is a probability of finding the electrons in between the nuclei is 0. That is, we are calling it as a node, where the probability of finding the electron is totally 0. That means the two lobes are being formed of opposite sign, which cancel each other. Therefore, the probability of finding the electron in between the two nuclei is 0 here, which we are calling it as a node or a nodal plane. And this results in the molecular orbital with the wave function of psi here, which is represented by U, un-G rate. I'll come back to this, what is G rate and un-G rate means. So this is what destructive interference. So subtracting, that means one is of another, two orbitals or atomic orbitals are of different sign here. So this is how the destructive interference is taking place. This is constructive interference. This is destructive interference. Yes. This is what is happening with the formation of the molecular orbitals, where equal number of molecular orbitals are being formed when atomic is equal to the number of the atomic orbitals combining. The number of molecular orbitals being formed is equal to the number of the atomic orbitals combining, and results in the two molecular orbitals here. One is represented with the wave function psi g and another with the psi u. What is this g and u? Let's see. Yes, and the probability of finding the electron here in between the nucleus is more here. That means that the electrons are held in between these two nuclei in the psi g here. That means this will stabilize the molecule, because the electrons are held in between the nucleus here. That means the nuclei which are present here are stabilized, because the electrons in between, there is no electrons in between here, therefore this is destabilized. There is a repulsion in between them two atoms, because there is no electrons holding these two nuclei. So positive will always repel. This is a nuclei. This charge is not with respect to the sign here, there's charge here, this is a sign, right? That's it. Okay, this is symmetry. So Now, the two electrons which is present in between the two nuclei will hold the molecules together by stabilizing it. Now, this results in the formation of what? Two molecular orbitals. One is called as bonding molecular orbital here. So here, this low, which is of lower energy, by addition in phase overlap, we are getting what? Bonding molecular orbital, and the other one is called as anti-bonding molecular orbital. Right. This is this is overlap, that means head-on overlap. The overlap is occurring here along the internuclear axis, right? Along the nucleus. Anyways, this S and S overlap is always head-on overlap only. So this results in the formation of here sigma molecular orbital is being formed here. This is represented by sigma and this is represented by sigma star. Why sigma star? Means this is higher in energy. So this results in the formation of two molecular orbitals, which is lower in energy, which is called as bonding molecular orbital, represented by psi. And the other one is an antibonding molecular orbital, which is more in energy when compared to that of this atomic orbitals, which is represented by psi star here. Right. So this is in phase overlap, so resulting in the formation of sigma molecular orbitals here, right? So represented by sigma and sigma star here. So now what is this G and U? G is for G-rate, U is for un-G-rate. What does this G-rate mean? G-rate means with respect to the symmetry. If the molecule is symmetrical, then we are calling it as G-rate. If the molecule is unsymmetrical, if this anti-bonding molecular orbital, then it is called as un-G-rate. So G-rate even, un-G-rate uneven. So how do you say whether the molecule is symmetrical or not? We can say this is symmetrical or not. I'll show you. So we'll know this with this symmetrical or unsymmetrical, that means G-rate or un-G-rate, if you carry out first of all, so there is two molecular orbitals which is being formed, right? This is bonding molecular orbital and anti-bonding molecular orbital. This bonding molecular orbital here is of lower energy. So we can know whether it is G-rate or un-G-rate. So this is G-rate represented by mu G. This is un-G-rate mu U. So first rotate the molecule along the internuclear axis. So rotating the molecule along the internuclear axis, and then again rotate the molecule here perpendicular to the internuclear axis. Rotate it twice, first along the internuclear axis and then along the perpendicular to the internuclear axis. First, when we are rotating the molecule along the internuclear axis, this is what is obtained. There is no change in sign. The positive just goes upwards, but there is no change in sign on the left and the right hand side. When again we are rotating the molecule here perpendicular, again the sign is the same here. So when you are getting the same sign when we are rotating it twice, that is first along the internuclear axis and then perpendicular to the internuclear axis, we are getting what? The same molecule. That means the signs are the same on the left and the right side of the molecule. So then they're there to be G-rate. So that is why the bonding molecular orbital here, this is a bonding molecular orbital here, it is G-rate. Right. What about this antibonding molecular orbital? This is antibonding molecular orbital. This antibonding molecular orbital here, first rotate it along the internuclear axis here, going to the upwards, but on the left and the right, their signs are the same, plus, plus. So no change in the sign. But when we are rotating it again, perpendicular to the internuclear axis, how do you get the signs here? So they are interchanged, change of sign. So this is, if the sign is changed when we are rotating it, then it is called as un-G-rate. So that is why we are calling it as, yes, I'll go back here. So rotate the orbital first. How do you know whether it is symmetrical or unsymmetrical? About the line joining the two nuclei, and the rotate about orbital about the line perpendicular to this. If the sign of the lobes remains the same, then it's G-rate. If the sign changes, this is un-G-rate. So this is what I said here, right? So Yes. So here, when you come back to this slide, there is a bonding molecular orbital. We are calling it as G ray. This is lower in energy because the sign, this is symmetrical. The sign does not change if I'm rotating it twice along the internuclear axis and along the axis which is perpendicular to this. But the antibonding molecular orbital is un-G rayed because the sign changes on rotating it twice. So it results in the formation of two molecular orbitals. One is lower in energy called as bonding molecular orbital, another is higher energy called as antibonding molecular orbital, that is un-G rayed here. So so here I said it is lower energy. By how much energy this is lower, let's look at it. Okay, fine. Yes. Now these are the two molecular orbitals which are being formed, that sigma bonding molecular orbital and sigma star molecular orbital, right? Now, so here, when this will stabilize, that means bonding molecular orbital is lower in energy when respect to the anti-bonding molecular orbital here. So when an electron enters into the sigma bonding molecular orbital, then it stabilizes the molecule, because here this is the electron is present in between the two nuclei here. So it will hold the nucleus together. So that is why it will stabilize the molecule here, right? Here, so the energy of this bonding molecular orbital here is lower than that of this atomic orbital by, and how much this energy of delta. This delta is called as what? Stabilization energy. So this is known as stabilization energy. Whereas the energy of an antibonding molecular orbital here is more in energy when compared to that of this atomic orbitals by the same amount delta. This is called as destabilization energy. So this will stabilize the molecule. That means the antibonding molecular orbital is lower in energy, whereas bonding molecular orbital is lowering energy, whereas antibonding molecular orbital is higher in energy when compared to that of this atomic orbital by the same amount of energy. Therefore, the electron which is entering into the bonding molecular orbital will stabilize the molecule by an amount of delta, and the electron which is entering into the antibonding molecular orbital will destabilize the molecule by the same amount delta. So for example, when I'm taking the hydrogen, so this is of the hydrogen molecule. So the hydrogen, it has single electron. This hydrogen atom also single electron. So when these two combine, the atomic orbitals combine, results in the formation of two molecular orbitals, that is bonding molecular orbital and anti-bonding molecular orbital. Right? So the electrons now first will occupy the lower energy orbitals, that is sigma. This is according to the rules. First, it will enter into the lower energy level. There are two electrons which are occupying this bonding molecular orbital. So I said the bonding molecular orbital is lower in energy when compared to that of this anti-bonding molecular orbital. So a single electron entering into this will stabilize the molecule by amount of delta. If there are two electrons which are entering into this, it will stabilize the molecule by 2 delta. That is why the H2 molecule is being formed. When H2 molecule is being formed, it stabilizes the molecule by means of energy which is 2 delta, which is nothing but the bond energy. That means this much of energy is released when hydrogen molecule is being formed. So this is lower in energy when compared to that of both the hydrogen atoms. That is why the hydrogen is being formed. So anyways, the molecule will be formed, or anything will be formed only when it is stabilized, right? So when it is stabilized, when it is lower in energy, when it lowers the energy by the formation of this molecule, so it is formed. That is why during the formation of the hydrogen molecule, here energy is released by how much? 2 delta. That is, this is equal to the stabilization energy. Actually, this is equal to the bond energy. So that means the energy which is released when the hydrogen molecule is being formed, that means it is stabilized. The hydrogen molecule is stabilized by an amount of 2 delta, which is lower in energy when compared to that of both the atoms, that is both the hydrogen atoms. That is why hydrogen molecule is being formed here. When we look at this H2, right, I said in the beginning of the molecule, in the beginning of the discussion, I said that H2, it could not explain why BBT could not explain why He2 molecule does not exist because of this reason. See, what is He here? How many electrons it has? 2 electrons, 1s2, 1s2. So if the bonding occurs, that means if the atoms overlap, atomic orbitals overlap, resulting in the formation of sigma bonding molecular orbital and anti-bonding molecular orbital here. So there are 4 electrons total. So the 4 electrons will enter 2 in bonding molecular orbital and 2 in anti-bonding molecular orbital, right? So results in the formation of 2 here. This is He, and this is He2, right? So right. So here the amount of energy, that means electron which is entering into the bonding molecular orbital, it will stabilize the molecule by amount of 2 delta. And also the electrons which are entering into this anti-bonding molecular orbital will destabilize the molecule by the same amount 2 delta. So these two will cancel each other. So there is no stabilization energy here. That is why H2 molecule is not formed. It does not exist. So this is the reason why He2 molecule. This is about the chemical bonding, and the rest of the chapter has been described on my YouTube channel, and the details of this has been given in the description box below.